Okay, so with that, I will wrap up and I will hand it over to our first speaker of the session, Mohammed Yama, who will be talking to us about the spectro-temporal law between sources of repeating fast radio bursts. So Mohammed, you want to share your screen?
Sure. Thanks, Emily. Hello, everyone. Is my screen showing okay? And my
Yes,
audio
it's great.
working? All right, thanks. So hi, my name is Mohammed. I'm a PhD student at Western University. I'm just starting my last year. Today, I'm going to be talking about evidence of a shared spectro-temporal law between sources of repeating fast radio bursts. This is work that we first submitted last December. And then there were some concerns from the referee about the robustness of the result, given how the DM is chosen. So we redid our analysis and we rewrote a lot of it. And that's what I'll be talking about today. Just to get started, I'm going to talk about the trigger dynamical model. So this is kind of a model we came up with to describe how we imagine the FRB process. There was an earlier talk by my colleague Fareshte Rajabi in the previous session. There's a lot more details there in that talk, and I will just be giving like a quick summary. So basically what we imagine for FRBs is we have a trigger and the source is in front of that trigger along the line of sight to the observer. We don't know what the source is. What we do assume is that it has some velocity and the source could be moving away from us or towards us. And most importantly, we assume that the FRB emission is happening at a single frequency, nu naught. So it's a narrowband process from the start. That's our assumption. And we also have a timeline for that process. So what we imagine happening is that there's a trigger that happens behind the source. And then there's some kind of delay time. And then after that delay time, the FRB emission begins, and that lasts for a certain time, tau w. So the model doesn't assume any physics about what tau d are, what tau d or tau w is. We just assume those times exist, but there's lots of room for extra physics to go into this model. These are basically all the assumptions that go into it. So what we do then is, assuming the source is moving relativistically, is we kind of transform this timeline into our own reference frame. So from the FRB reference frame into our reference frame. So that's just a Lorentz transform, and then you take into account a relativistic Doppler shift, and we can derive this relationship between the subburst slope and drift rate. I'll talk about slope in a second. And it's in terms of the frequency that we observe it at, the FRB at. This term here is the slope and sometimes the drift rate. And then we have this constant out front, which is in terms of the times. And it's inversely related to the duration in our reference frame of the FRB. Okay, so let's talk about what I mean when I say slope versus drift rate. So this is some terminology confusion that we had early on, but so I just want to make sure this is clear. So I have here some data from Gajar. It shows multiple bursts within a single FRB, multiple subbursts. And when people talk about drift rate or sad trombone, we're talking about essentially drawing a line between the center frequency of each of these subbursts and measuring the slope of that line, roughly speaking, or essentially that's what's happening. And really what we were trying to study was the slope more particularly. And the slope, what we mean by that is just basically the same thing. So frequency over time, but within the individual subbursts. So for our model is mostly predicting things about the slope. There are predictions about the drift rate, but we really want to focus on the slope to start. But we will see that these two measurements, while at first they seem distinct, can be closely related. So how do we obtain these measurements? So we're using the autocorrelation technique that was described in Hessel's 2019. Where basically you take your fast radio burst, your waterfall, you compute the 2D autocorrelation of it, which will almost always give you a nice elliptical Gaussian-like shape that you can fit a 2D Gaussian to. And from the fit parameters of that fit, you can get things like the subburst duration. You can also get the angle that the Gaussian is rotated, you can use that to calculate the slope, the subburst slope, as well as the drift rate if there were multiple subbursts within this waterfall. So this is a good technique because it's repeatable, it's easy to automate, also handles fast radio bursts with complex structures. You can have strange shapes, but you'll always get something that is more elliptical and more Gaussian once you compute the autocorrelation. So when we want to measure these parameters, the question you hit immediately is, what DM should I use when I'm measuring when I'm measuring these things? And the reason that's important is because if you have a waterfall and you'll just vary the DM you've chosen even slightly, you'll rotate the autocorrelation function, which will change the value you get. So for example, for the slope, of course, over here, I'm going to get a very large number for the slope. It's very steep, and here I'll get a much larger number. So, that's a big problem. You can get like a huge range of measurements based on your DM choice. I have here an example also from Gajar 2018, where they talk about two choices of DM. So here you have a fast radio burst, and it has several bursts within it. And if you choose a DM that's found by optimizing the signal to noise ratio, what the algorithm is going to do is it's going to stack the components of the fast radio burst to increase the signal to noise, and you'll get a DM that's high. So in this case, you get a DM that's 600. But if you had a different algorithm, like if you chose a structure parameter and chose to optimize that, which would preserve the structure of the FRB, and you choose a DM that way, you're going to get a DM that's much lower. So in this case, you get 565. So this is a choice this is a problem you have to deal with when you're trying to decide which DM to choose before you perform your measurement. One thing you could do, so we're trying to look at as many bursts as possible. So one simple way is to just take the published DM for each burst and use that and hope things work out. But there's a problem because a lot of these bursts are not available at very high time resolutions. So it's hard to tell if they're resolved. So here, for example, it looks like there's maybe 2 bursts here. And then as soon as you don't know if your FRB is resolved, it's really hard to decide between a structure optimized DM and a signal to noise DM. So my answer to the problem of what DM should you use when measuring an FRB is, why not all of them? So what we do is we just pick as many DMs as possible. We pick a range of DMs, and we're trying to be as conservative as possible. So we want every plausible DM, and we're going to repeat our measurements at each DM. And this is going to give us a range of measurements across the DM range. So this is going to give you very large ranges. So it's going to be a large range of measurements, but it turns out to be accurate enough to determine if the relationship the prediction that we've made with our model describes the data. So that DM range is going to be chosen based on the history of the source, how it changes with time. You can look at the sample of the bursts that you're using, see the distribution of the DMs that were found. And there's a few little tweaks you can do, but basically you're just trying to pick as big a DM range as possible. And this will help us assess the quality and the robustness of our results. Okay, so what we did was we took 41 subbursts from 3 different repeater sources. They're listed here, 121102 and 2 sources that were made available by Chime. And across the DM range that we chose for each of those sources, we found valid measurements at each DM for 28 of the subbursts. So 28 of the subbursts, when you try to measure the slope, you're going to get a reasonable number. And those are the points that are most displayed here. The remaining points are circled. So these needed a slightly shorter DM range. And what I mean by valid measurements is basically avoiding the discontinuity that happens when your slope is infinite, when your FRB appears to be vertical. or positive. I forgot to talk about that. I'll come back though. So yeah, so here I have the prediction from our model, and there's a negative sign here. So we expect every slope to be negative. And if you want to understand this physically, what's happening is you always expect the lower frequencies to arrive later in this model because it's a relativistic model. So the lower frequencies will have a longer time dilation, and that's why they should arrive later. And that's why we should always expect a negative slope. But what we see here, so notice the scale and notice the bars on each of these points. So the bars are not uncertainties. They are the range of measurements that were found. And we argue that these ranges are much, much larger than the true uncertainties. And this is just because of how large of a DM range we've chose. And even with these massive ranges, you can see that there's a very definite trend between the three sources. Using the range of measurements, what we also do is we'll find a fit for each DM, and we can find a range of fits similar to how we found a range of measurements. And those are shown in the shaded regions. So note how the shaded regions are close to each other, they overlap, and there seems to be agreement between the three sources. So the real point here is that the existence of the trend is independent of DM choice. And this is true even though the measurement of each of these slopes is very dependent on the DM choice. But we can still see that the trend still exists, any DM choice. So I want to talk about, so if you look on my axis here, I've labeled it as slope, but are these really all slope measurements? And I have an example here of what the real problem is when you don't have a high enough time resolution in your data. So here's an example of an FRB with multiple subbursts. But at the time resolution that we have, it looks like a single burst. It's basically almost impossible to tell. It can be impossible to tell if the FRB you're looking at has multiple subbursts or is just a single subburst.
3 minutes.
So if we, 3 minutes, okay. So if we were to put this through our pipeline, we're gonna get a slope. We're gonna call it a slope, but really it's a drift rate. So how come we don't see many, in our plot, how come we don't see many deviations from the trend or outliers, many outliers? Why aren't there two populations, one for the drift rates and one for the slope? So in our model, it's actually okay. The drift rate can follow the same trend as the slopes. They will be longer duration just because they're consisting of multiple subbursts, but they will still follow the trend. And that happens because they have similar delay times as the individual subbursts. So the model is a narrowband model in nature, and we can use it now with our fits, the fits that we found to make very rough estimates of the physical parameters. So for example, the rest frame frequency we can find based on the range of frequencies found, observed for this source, which range from 110 megahertz to almost 8 gigahertz. We can deduce that the rest frame frequency is about 1 to 2 gigahertz, and we can find other parameters like the velocities. So at the highest frequency, we expect that the velocity of the source, the emitting source is, parts of the source is very high, 90%, almost 90% the speed of light. And the bandwidth of the source is also related to the velocity. So it's directly due to the velocity. Excuse me. So in our model, the way we kind of, if we put our model glasses on and look at a waterfall, what we see is these individual subbursts, and we're going to try and understand that each of these different frequencies is coming from a different velocity sample within the emitting source. So the material that is emitting this part of the signal is moving a little faster than the material emitting this part. And yeah, so that's what I wanted to talk about today. So the existence of the trend, we see it regardless of the DM chosen for each burst. But of course, the DM choice greatly affects the individual measurements and the fit that you will find. So obviously the next questions that we want to answer is, do all FRB repeaters follow a version of this relationship? If not, are there going to be different classes between these repeaters? Did we just get lucky with the first three sources and they seem to line up? And then importantly, we want to use this eventually to find physical parameters of the source, like the rest frame frequency of emission, which will tell us about the emission, the underlying emission mechanism. So there's lots of data becoming available with much better time resolution. So that's great. There's the CHIME catalog with tons of new data. So some very early results of a fourth source that we've added. This is from 180301A from Luo et al., who I believe is giving a talk later in this session. So just some early, very, very early results, just to show how that fits with the other sources. But there's lots of data becoming available, and we need tools. So this is an interface I've been building using DearPy GUI. It's very fast, very lightweight, and it'll hopefully help me analyze the amount of data that is coming out of CHIME and other big telescopes. So yeah, that's all. Thank you very much. Check out these packages. Thank you to the CHIME website for their help with the data early on. Ziggy Plunis and Sriharsh Tendulkar for their emails. And yeah, thank you.
Thanks, Mohammed.
Yep.
We already have one question in the Q&A. If you have other questions, participants, please feel free to put them in the Q&A now. So the first question is, how does this DM selection give results for highly periodic repeaters compared to the repeaters with lots of uncertainty in periodicity?
Sorry, could you repeat that? How does
it? So how does the DM selection, how does this DM selection give results for the highly periodic repeaters compared to the repeaters with lots of uncertainty in the periodicity? I guess, do you see like that the sources that have been found to have an underlying periodicity, do they like follow this relation more closely, or?
Well, the only sources we've looked at are these three. I believe 180916 has a periodicity. I don't know if the other two have a periodicity.
Yeah, 121102, it's like a tentative sort of like several 100-day periodicity. So.
Oh yeah, okay. Yeah, I guess I don't really know how to answer that. I don't think we have seen much of a difference based on what we've looked at.
No, that's great. Okay. Other questions? Okay, another question in the Q&A. Aaron Perlman, do extrinsic effects, e.g. frequency structure introduced by scintillation, impact this analysis?
They do not. I don't have a good argument. I remember we talked about this in the paper, but the scintillation will essentially not show up in our relationship. And that has to do with, it has to do with how we derive this. But I'm sorry, I don't, maybe in the Slack you can, yeah.
No, that's okay. You can, okay. And then the next question in the Q&A from Sergey is the huge data set from FAST about FRB 121102 available for such studies? It is better to look at large statistics from the single source.
Yeah, so I do have a lot of 121102 data that I'd like to get to. There's data from FAST, I believe, and there's also data from a lot of other sources as well for 121102. Yeah.
Okay, and then we have time for one more quick question from Bing Zhang. How does the relation look like if the redshift 1 plus Z factor is considered?
So because we, I'll go back to the model here. So this term here, we have d nu obs over nu obs. And basically we present the data this way because the redshift correction that you would have to make cancels out once you show the data this way. So we don't have to worry about it. How does it look without? If we were to do the redshift correction, so if we were to move this nu obs over to the other side, you would basically have a vertical shift between these slopes. Yeah.